in this question, once again, we have, this is a mass stress pulley. String goes over like this. This is spring of spring constant K. And this block of mass M is now just being held like this. So this is not equilibrium position. This represents the position when we are just going to fix this mass and we are going to tie it to this string. So there is no extension in this spring right now. That is, spring has a natural length and there is no extension over here. The second is, as we did earlier, this is the equilibrium position we are talking about. That is, it has gone by some distance. As a result, there is some extension also in this. When we say it has gone by distance x, it means the pulley also has gone by distance x. This is from this, pulley has gone from this level to this level. This is a string, this is an inextensible string. So this, if this block goes by x, the center will also go by x. If the center goes by x, the pulley requires a string over here also and on this side also, this side also and this side also. This string cannot extend. It is only this can stretch. This can stretch and compensate for the extra requirement of x thread over here and x thread over here. So it means when this block it goes by distance x, then the stretch in the spring is x required here, x required here. So 2x is the stretch in the spring. And when we are talking about equilibrium position, certainly the whole thing is stationary axis is equal to 0. It means the tension in this whole string and spring is same because the stretch is 2x. So as a result, the tension in this string and spring, it is going to be k into 2x. K into 2x over here, k into 2x over here, the t is over here. This pulley is massless. So it means this plus this is equal to t. So t comes out to be 4kx. Now we consider this block. T is over here, mg is over here. So t is equal to mg because right now we are talking about the equilibrium position. So when we say t is equal to mg, so 4kx is equal to mg. So over here, now we consider when it has moved from here to here, that is from this level to this level it has gone, y distance it has covered further, and it is going to cover some further distance also to reach its amplitude. That is from here to here, it is going to be some amplitude, it is reached over here only, where it has some velocity also, and from this level it has gone y distance further below this level. When it goes further distance y, as a result, the stretch in the spring further increases by 2y. So now the total stretch in the spring is, when it had gone x, so the stretch was 2x. Now when it further goes by y, there is a further stretch of 2y. So now the extension in the spring is 2x plus 2y, that is a total stretch in the spring. And the velocity of the block is v in the downward direction. Now let's use energy conservation method to find a time period of the oscillation. We say extension is 2x plus 2y and this block has gone x plus y from its original position. That is, initially it was over here. Now it has gone from here to here. That is x plus y. Total is it has gone x plus y from the position when it was just tied to this string. So over here we consider what are the losses and what are the gains. So this is loss in potential block is mg x plus y. This is the loss. It has gone from here to here. It has gained some kinetic energy, is half mv square, and there is certainly gain in potential spring, that is half k, and the total stretch is 2x plus 2y. So total stretch square. Then we say that is loss is equal to gains. So it comes out to we put loss is equal to gains and we follow the usual steps. Then we differentiate with respect to time. Obviously that is mgx, this term, x is constant because this is a we are talking about the equilibrium position. So mgx, x is a constant term. If we differentiate it, this comes out to be 0 only. So dy by dt stands for only for velocity only. And when we are going to differentiate it, this comes 2v dv by dt, rate of change of velocity is acceleration, and we get some expression. Over there once again, when we write this equation, after this we may have to make some substitution from our reference of this equilibrium position. That is because over here we see that is there we have mg also and we have 4kx also. That comes out to be. That is term in x is also coming and mg is also coming. So what we do is over here we refer to the equilibrium position. And from equilibrium position we find that is 4kx is equal to mg. We can substitute or we can directly cancel it. And then we can get that is 0 is equal to ma plus 4ky, a comes out to this thing, x is in proportion to minus y, so this comes out to be shm, so t is 2 pi under root y by a, 2 pi under root m by 4k, that comes the answer. So this is how we can use energy conservation method to find the time period. We can also find the time period by displacing the body from its mean position by distance y, then talking about the restoring forces, x is in proportion to y, and so on. Let's have a look on that. This is initial when there is no stretch in the spring, this is natural length, there is no extension, so we are just holding it. Here we are talking about the mean position of block, that this is the mean position of block when it has gone x below this level, and this is the mean position. Right now there is no net force which is acting on this body. Pulley is massless. When it goes by x, so obviously the stretch in the spring is 2x. So when we talk about the equilibrium position, we say over here k into 2x, because stretch in the spring is 2x. So k into 2x, k into 2x, t is over here, pulley is massless. So this plus this is equal to this. So t is equal to 4kx. And we look over here, that string is same. So the same tension is throughout the string. So t is here, mg is here. So t is equal to mg. So we get 4kx is equal to mg. This is the equilibrium position we are talking about. As usual, displace the body by a small distance y from its mean position and look for the restoring forces. When you pull a distance further by distance y, then certainly there is stretch. Once again, there is a further stretch in this spring, and the stretch in the spring is, once again, it's going to be 2y. It has gone from here to here. Y string is required here, y string is required here. The string is inextensible, so as to compensate for this y and this y requirement, that is 2y requirement, this spring stretches further. So now the total stretch in the spring is 2x plus 2y. Tension in the string is k into 2x plus 2y. If it draw the free body diagram of this pulley, t is here, t is here, t dash is here, t is equal to this thing. So t dash is twice of t. And if we draw the force diagram for this, so t dash is here, mg is here. So t dash minus mg is equal to ma. So it comes out of 4kx plus 4ky minus mg is equal to ma. So now once we have this equation, now over here we have 4kx also, mg also. So now we refer to the equilibrium position where we have 4kx is equal to mg. So this and this gets cancelled. Ma is equal to 4ky, x is equal to this thing. And we also know that is when we pull it down, this will accelerate in this direction. Displacement has been in this direction. That is, it is oppositely directed, and from there we can find the time period. We can also find the time period without getting into all those things, but certainly these things, they are important to understand the concepts, that is what is actually happening, what are the forces which are being applied, and how we are using the energy method. And if we are just bothered about the answer, so what we do is, once this is the mean position, that is once this is stable, we directly pull it by distance y. We are not bothered right now in equilibrium position, that is what are forces which are being applied, what is the stretch in this, what is tension in this, we are not bothered about it. All the forces are balanced, and now we pull it by distance y and we look for the extra restoring forces now which come into play. When we pull it by distance y, then certainly this pulley center, this goes by distance y, and now the stretch in this is 2y. If 2y is a stretch, the tension over here is k into 2y, k into 2y. So the extra force, extra restoring force which is generated in this is 4ky. We say 4ky is equal to ma. That is, we get the same thing. And from there, acceleration proportion to minus y, and we can get the answer. So over here, what we have done is, we have not considered is how the mean position has been achieved. We have not considered much about the forces at the equilibrium position, that is when the system is in equilibrium. We have not considered the forces. What are forces which are acting on this body or on the pulley? From the equilibrium position, we displace the body by distance y. And when we displace the body by distance y, we look for the extra restoring forces. That is, what is now the extra stretch in this spring, what is the extra restoring force comes over here, and what is the extra tension which is generated over here, and we put directly is equal to mass into acceleration, and from there we can proceed to get the answer.